Tonight we're going over 1678's 2022 robot that they built for Rapid React, the 2022 game. So we all have an idea of how that game worked. We're going to go ahead and play the game animation video. Just a second.
Welcome to the 2022 FIRST Robotics Competition. And this year's game, Rapid React, presented by the Boeing Company. Two alliances of 3 teams each compete to score their cargo balls into the lower hub and the upper hub. They earn additional points if the robots traverse the rungs of their hangar. Robots start each match on one of their tarmacs and may be preloaded with 1 cargo each. During the first 15 seconds, robots are autonomous. Without guidance from drivers, they leave their tarmac, score preloaded cargo, and collect and score additional cargo. During the remaining 2 minutes and 15 seconds, drivers control their robots. They continue to gather up 2 cargo at a time and score cargo in the lower and upper hubs. Cargo scored into either hub count towards the cargo bonus. Launch pads protect robots from contact by opponent robots. Robots may use either terminal, where their human players assist the robots with acquiring cargo. As time runs out, robots race to their hangar and traverse as many rungs as possible. The higher a robot gets, the more points it earns. An alliance that reaches a hangar point threshold is rewarded with a ranking point. The alliance that earns the most points wins the match.
All right. So relatively simple game, right? We basically have to pick up our colored balls. So whatever alliance we're on, if we're on red, we're picking up the red balls, launching them into the goal. If we're on blue, we're doing the opposite. And then we have this hanger contraption that you have to climb at the end. And the rules there were very specific. You weren't allowed to just extend up and grab the highest rung. Like you wouldn't. There was a very specific amount of reach you were allowed to like extend your robot to, of how long or tall your robot could be. And so you had to fit that requirement. And because of that, it basically meant that you could only grab what they ended up calling the middle bar, which the bar names were really annoying this year. It was low, mid, high, and traversal, because they decided they had 4 and they wanted to start it low. So you could grab the mid bar, and then you had to get your robot over to the traversal bar. And so there was some amount of like monkey barring to be able to do that, and teams solved it in a bunch of different ways. We'll look at it at some other point, but there was one very creative solution that year that is not this robot. There's a robot that actually figured out how to jump up and grab the traversal bar. That was very interesting. So there's a lot of ways that you can think outside of the box and do this. But part of the goal, anytime we're looking at how to design robots to do this, is how do we make something that's fast and reliable, and packages into the rest of the robot nicely for all the other tasks that it has to do. In a lot of games, and this one as well, the low goal ended up not mattering all that much in terms of high levels of play, whether you're going to win or lose a lot of matches. And so really you weren't focused on scoring in the low goal. It was possible for most of the launching robots who could score in the high goal just to launch shorter and score in the low goal, but it wasn't really a design requirement. You weren't really trying to focus on that. You knew that to win events and to eventually do well at states and worlds, you needed to be scoring in the high goal. So it was a pretty easy list of the basic tasks the robot had to do. But then teams are able to take that and build a whole lot of different robots that all accomplish that task in different ways. Today we're going to look at Citrus 1678's robot. It was one of the better robots. Citrus is always known for building relatively simple robots that are pretty much, they are very efficient at getting the task done. They're not going to add too much complexity unless they need to. And so they, pretty much all of their robots kind of follow that same principle. So we can watch their robot actually play the game before we dive into the CAD and see how they actually designed it and how they built it. So this is that citrus robot right here. Why did it get to horrible quality? There we go. So that was all autonomous, and now they're on the Blue Alliance. They're picking up the blue balls. Kind of briefly see it. This was definitely a pretty chaotic game as everyone's scoring into the main center goal. So you don't have kind of the normal cycles and things that you do in other games where people are going one way and coming back down to shoot or anything. Everyone's pretty much just picking up where they can and immediately being able to fire. Software was pretty important in this game, being able to aim at this target ring. This is before we had April tags, so we didn't have full on-field localization, so it was not as easy to know where your robot was, so you didn't know where the goal was at all times. So that's the first time we saw them. They have a feature on their robot that they called the pooper, because if they picked up the wrong color ball, they would basically spit it out the front of their robot. So they could still intake the right color ball without having to like push it back out the intake. All right, now they're setting up for their end game. So they pick up onto the mid bar, and then that one latches the high bar, and then they pull over onto the traversal. And so part of that is to be able to do it really fast, which is part of why they designed that mechanism the way they did, was to be able to do that end game climb in sub 10 seconds, and they were much faster than that. All right, so we can look at the actual robot. So coming in, we see just like every other robot, we can kind of divide it up into mechanisms. They do a similar thing here. So we have our drivetrain, which again, in this kind of modern era of FRC that we live in now, pretty much from 2022 forward, a lot of the drivetrains are pretty similar. So we have the drivetrain. We have the intake here, which we'll talk about. This is to get the balls up into the robot. They have what oftentimes is called like the indexer, where basically you're able to put the balls in order, get them ready, store them, ready to go into the launcher. This also has the wheels that are designed to push out any of the wrong color balls. And then we have their launcher mechanism up here on top. So this is just the hood. So the launcher is kind of built in to part of how they did the indexer, because these are just where they're able to like separate them, because this part up here can be taken off separately from the rest. So they designed them in like two different ways. They designed this as the hood, and then they integrated all the rest of this. We will split it up a little bit and talk about launcher and hood together, separate from indexer. And then we should have the climber here as their last one. On the side of their robot, and that's one of the advantages that Swerve gives you, is you don't have to necessarily build it at like the front or the back or anything. You can do it out to the side, because it's easy enough just to drive sideways for any of those tasks that you need to do just at the end game. All right, so let's hide everything but the drivetrain, and let's dive in and see if they did anything interesting. So this actually includes part of their intake or ball sorting mechanism. We have a couple wheels sticking up here that are designed for the balls, not just for their drivetrain. But it was part of it because they needed to use the belly pan and things to mount everything here. And so they used it as part of their drivetrain. So backing up, let's go over kind of the generic features of a robot when we just start staring at it. This is a swerve robot. It has the modules in the corners. And so we have these 4 wheels, one in each corner. Each wheel can steer and rotate. Um, these are just generic swerve drive specialties, MK4i modules, the same swerve modules that we've run on all 3 of our robots since 2022. They're pretty much one of the de facto standard ways to do swerve. They work, they're reliable. There's haven't been much updates or anything to them. And they're pretty much going to be the same on any robot that look like this. Um, in addition to that, they're running the same like standard 2x1 frame, where they just have the aluminum tubes on each side, and that pretty much builds up the main structure of the robot. They're running a central crossbar that's actually a little bit bigger. So if we look at this, it's a full 2x2 cube or square profile instead of a rectangle, going all the way across. So it gives their frame um, some support through the middle here. So you're not going to like bend these frame tubes, and it gives you a lot of mounting locations right through the middle of the robot, which is very convenient and useful for them. Because they actually have a split belly pan. So we have the one side that's kind of on the lower end, where we would normally mount our belly pans for our robots. And then they have this upper pan over over the front half over here, um, that is commonly referred to as a brain pan instead of a belly pan, because it's on top of the drivetrain or on top of the drive rails, and this lets you mount your electronics underneath. Um, there's times when this is advantageous. It kind of depends on how you need to get to things, how you want to design it. But this lets you just pull this little polycarbonate plastic panel off, and then you can get to your electronics by kind of flipping the robot up onto its back or side, and you can get to the wiring and get to things like that. Most of the time, we prefer to not do this. We prefer to find a way to have our electronics on the top side. Sometimes we'll have to, tuck them in somewhere, but we're normally pretty okay to have them on top and then just have panels on top that we can remove, and still get enough inside to do it. There's not too much risk of anything coming in here and damaging them or anything, um, but it's just kind of preference. A lot of teams have done this and been successful. It just sort of depends on how you want to do it and what the design constraints are for the rest of the robot. Um, Similarly, they have some things that are pretty standard, normal, like battery mount here. Um, I think, yeah, so this isn't going underneath or anything. They're mounting the battery in from the top and just laying it down to be able to plug it in. But then they do have the side roller omni wheels. So an omni wheel is a wheel that has these extra rollers here that can spin perpendicular to the normal rotation of the wheel. And this lets, either if it's on like a drivetrain, it lets you like slide sideways and things. But it also lets you, on this specific case, allows the ball to move up and down and not like rub if it was like a normal wheel. So it allows it to fall into place correctly, and then still be able to kind of get pushed into the center here. So if the ball gets intaked up to here, this can spin it in, and get it shoved into the center correctly. So they don't have any jams or anything like that as they're trying to intake multiple balls into this center column where the rest of the ball path's going to be. And so they did that with a few standoffs from the belly pan. So they have all of these standoff rods here that are either, some of them are tapped or through hole depending on where they're going, to get bolted all the way through. Or they might be bolted all the way through, actually, I'm not sure. Yeah, 191. So those are probably bolted all the way through, and just with long bolts. They'll have nuts on one side and bolts going all the way through, it looks like. Okay, so yeah, very simple mechanism, basically just a motor on standoffs. It has a small pinion pulley and a belt driving this larger pulley, and then just hex shafts here um, on each side. And then the only kind of unique thing is they do have a chain and sprocket running on the underside of the robot to be able to transfer power underneath where their battery is to the other side. So you could have done the same thing. You could have had like a belt running right here or something, but then you're like in the ball path. You could have run it a little bit farther under, but it makes it harder to put in and out the battery. So doing it on the underside keeps it out of the way, but still lets you easily transfer power to the other side. And then they need this gear or these two gears right here to be able to reverse the direction of this wheel compared to this one. And so you can have them both spinning the balls in towards the center. If you just had that chain on this side, they'd both be going the same way, and this one would be wanting to spit the ball out to the outside, and you don't want that. Um, so using the gears here to reverse, we've seen that in a couple other robots. We've built robots that use this technique quite often. Anytime you just need to reverse a roller from the direction of the rest of the system, two gears gets you that setup, or any even number of gears gets you a reverse direction. Okay, what else do we have here? So they have a couple little sensor mounts and things here. The rest of this we'll see as the whole ball path, but these are sensors. These are called beam brakes, so that if an object comes through and stops one side from seeing the other, the robot can detect that. These will be plugged into the RoboRio, and then we can see them in software that we can know, oh, this is there's some object here. In this case, the ball's there, and so we could use that to sequence the rest of the rollers and build up the commands to tell the robot how to move the balls through the robot, so the pilot isn't having to do all that, or the operator. You can automate a lot more if you have sensors like that. Uh, Everything else is pretty standard. They do have a cool little 3D printed um, RSL robot single signal light mount here, so they are able to mount the signal light directly to the belly pan here. This is probably just zip tied on, um, and so they didn't have to put that anywhere else. They were able to just do that right on top of the brain pan that they made here. Um, Citrus does use the same bumper mount style for the last couple years. This was inspired by the way that 971 did it in 2019, I believe. I think they were one of the first teams that we've seen do this. So inside these holes, there'd be a stud that's mounted to the bumpers. So they basically have a bolt sticking through this. And then on this side, you have a nut that you're able to turn down, and it just clamps this plate. And so they do that in a few places, um, front and back. And then I don't know if there's one on the side. Yep, there's one over here on the side. And that just securely holds your bumper with that clamping force. Um, you'll see some teams also like counter bore this, to where they'll take out a little bit of the material here and leave some on top. So it's like the nut goes in, it can't come out even if it gets a little loose. It's not just relying on the clamping force; it actually runs into something too. You'll see some teams add that little pocket there to help secure them. But it's a relatively um, standard-ish way to mount bumpers now. Teams have started doing it. Our 2020 robot used this method, and it worked very well for us. Okay, moving up, we get to their intake. Let me hide the bumpers here if I can. Let's see. Kind of. There we go. Okay. So without bumpers, it should be a little bit easier to see into the robot. So we can kind of see how their intake is mounted. They have these large intake plates on the side here. These are going to be 1/4 inch aluminum most likely. Oh, actually they're running 3/16, so a little bit thinner than quarter. Um, but still probably plenty strong. They probably didn't bend this too often. Um, And 3/16 does save a good amount of weight, right? Compared to a 1/4 inch plate, you're saving 25% of the weight. Um, so as we're designing, when we can, using 3/16 or something is often a little bit better on weight savings. There's no mounts on the inside of the tube at all. So if they need to take their intake off, they can just drill out whatever rivets here on both sides, and the whole thing could come on and off without having to do any work on the inside of the robot. So this plate doesn't extend down, it doesn't like sandwich it at all. Everything else is just stood off directly from this outside plate with these different standoffs, or cantilevered directly on it. So like this plate or this sprocket doesn't have anything supporting it on this other side. Um, Zoomed out a little far. Um, so we call that cantilevered. It means it's only supported on one side of the shaft or whatever the object is. And so this is just going to be bolted in here. This little shaft and spacer setup with the washer is just going to be bolted directly to this plate. And so it does have the ability to potentially like bend or something since it's not supported on this other side. But since this is thick enough, this is down low, and this is a polycarbonate arm, so it's not going to transfer all of that load directly into here because the plastic part here will bend first before you're ever going to be able to bend this aluminum plate. It ends up working out pretty well. And so they did have to package this really tightly, right? So the chain that's running right here has to get really, really close to their swerve module pulley that does the steering. But they did make that work. But this is why we definitely have to CAD all of our mechanisms. It's why we add like belts and chain and things into CAD, because you can get very, very tight tolerances. But it is clearance. It's clearance in real life as well. Like these two things are not going to hit each other. And so it does work, but you do want to be careful when you're getting anything that close that you are checking things, that your like CAD geometry for the chain is correct. This may be a thing that you want to like test in real life before you commit fully to it to make sure it does fit. Right, we could laser cut one of these plates out of wood real fast, bolt up a sprocket in the right stack up to it, with all the like the pieces and things it's going to need to get the right distances, and make sure it doesn't hit the pulley in real life. Because CAD can be a little bit different sometimes from real life. So anytime we're that close, we'd like to check and make sure that we're doing it correctly. Especially if there's not an easy way to move one of the two things. If we think this is the way it has to work, you definitely want to check your tolerances. Okay, so coming up from that like mounting plate, we can kind of see the gearbox that they used to actually do the pivot. So they built it all into this outer plate and this inner standoff plate. So it's relatively simple. They just have a small pinion gear here that goes into a two-stage gear reduction. So you get this shaft, the center shaft's running a little bit slower than the motor, then you run it a little bit slower again. And on this one, they have the shaft crossing the whole robot. This is commonly referred to as like a jack shaft, so it's going to the whole other side of the robot, and that lets you power it both sides of the intake instead of only having like one side moving. You get it symmetrical. That lets the intake move in and out a lot smoother. Um, if anything causes resistance or anything, you have power on both sides to kind of make sure both arms are coming up equally. That's normally a lot better than trying to only power it from one side. Powering it from both sides is normally a much better option. And so they do that by having the sprocket here on both sides of the shaft. And then we go over to our larger sprocket that's actually bolted to the polycarbonate arm. And this is what allows us to actually drive the intake in and out. So as that sprocket rotates, this whole mechanism drives in and out. And we get that motion of being able to start fully in our starting size limit. So we have to make sure that no part of the intake passes the front of this plate, basically. That's going to be where our frame perimeter is. And so wherever our starting configuration is for this, we try to make sure nothing of this part passes here. And then when the match starts, when we're ready to deploy it and grab a ball, we can spin that motor and push out this roller, so the ball can get sucked up through each of the three of these rollers and then into um, the centering mechanism that moves the ball into the center and then gets it up into the actual robot and get it ready to launch and fire so we can actually score points. Okay, let's see a couple bits about this intake. So this is commonly referred to as a 4-bar intake. The reason for that is it's the type of linkage that's used here. Um, One of the misconceptions about these is they think it's called 4 bars because of these 4 bars. That is not the case. Each side of this mechanism is a 4-bar linkage. And so really it's like the lines between the pivot points that you're considering as a bar. Um, so like this bar down here between this hole here that acts as one pivot point and this hole here that acts as another, it's stationary. It doesn't move at all in relation to the robot. But this is like your first bar, your first link. And then you have another one that goes from this pivot point up to the top up here. Um, you have a third that is between these two pivot points here on this the actual like intake plate. So the distance between those two pivots, and then one that comes all the way down again on this other bar from here to here. So because this kind of makes like moving trapezoids-ish parallelograms, um, you get that you're able to get that motion based on rotating one when you can't change the distance between these four things. Like any one bar doesn't change distance ever, but they do change how they're related to each other. Um, and when we go into CAD to like design something like this, we're able to kind of figure out where we need our rollers to be and how we want them to be placed. And we can figure out where these pivots have to be to give us the motion that we want, um, to get us to where this roller's at the right height to be able to like suck in the ball. This one's there to be able to move it up the bumper and everything. And we can figure out how to make that nice in and out motion work, to package it in a nice small spot when it needs to be fully retracted, and then deploy it nicely as well to let the ball in. They did some nice things here. You can kind of see they designed in the arms to basically be able to nest into each other or meet. So as it's up, this goes away from it, but this curve is exactly designed so that when it is fully down, it acts as a hard stop, and it stops this arm from going past here, um, and it makes it a little bit more stable. And then similarly, when it comes up, this arm here nests into this one as well in its up position. And so you can kind of see how it's cut out right there to act in those two different ways. And so it's relatively easy to do in CAD. It would be very tricky to do if you were trying to make that by hand, but you can CAD them in the two different positions and add in the parts that we need, to make that motion work very smoothly. Okay, let's look at the other side so we can see how the rollers are powered. So again, this is the pretty common pattern of just having a motor on standoffs from that plate with a pinion on it. In this case, it's a pulley that they mount here. It looks like ended up needing a little bit more speed, so they ended up using a bigger pulley, that has a 1/2 inch like hex, so it's normally goes on a shaft instead of on a motor. And so they used an adapter that you can get that goes from the motor output spline shaft here, to a hex shaft, so you can drive a bigger pulley if you want to. They also did use a full metal plate here. Let me see if we can isolate that. Yeah, so that's just there for to help with mounting, it looks like, but that still has to go all the way through. So they're still using the motor as those mounting holes, it looks like, since there's only the three mounting holes. Yeah, I'm not entirely sure why they have that plate there. A lot of times you can use just the motor, or a 3D printed part to help offload some of that weight or some of the load to make it so that the motor can't bend at all or anything. That might be what the ring is doing here on the outside. Um, they may have had some reason to do that. I can't quite tell from CAD what that is. Okay, so they have a belt though that comes from that pulley and goes up to a larger one to give you the reduction, so that again you have these rollers spinning slower than the motor. And then they have these nice large pulley flanges so that the belt can never skip off, especially when you have um, a belt run here that's only mounted on this polycarbonate arm. Because this can flex, the distance that this belt is actually, the distance between these two pulleys changes a good amount, especially if this is ever gets like run into. If you slam this into a wall, um, this is plastic, so you can imagine this arm could bend out or in a little bit. And now this pulley can get closer to this one down here, which means the belt doesn't have as much tension on it. And so it can skip over if you just had a tiny flange like you do down here. The belt potentially just like skip off, and then you can't intake balls anymore because you don't have any power going to spin these rollers. Um, and so what they did to solve that was they made really tall flanges on the pulley that they printed here. So this is just a printed part, um, likely printed with supports here on the inside that they'd have to remove because you can't print this like full overhang. You can't just print this into thin air. So if you're building this up from the build plate on this side, um, you would need something to support it so that once you get to here, you can print this surface without it just falling down. And that normally works pretty well. You do end up with a little bit of a rougher edge when you have to remove the supports, but you can dial in the settings and get that pretty good. Anytime you see this little like flowery sort of gear looking cutout, but it's not, doesn't actually look like a gear. This is a Thrifty Bot 3D print insert. So this is a cutout that allows you to shove a metal insert into here that lets it have a stronger interface to the hex shaft. So you can't do what's called rounding out the hex to where the hex shaft itself could end up spinning inside of the hole and the pulley wouldn't spin with it. So you can basically make this hex hole big enough so that the hex can just rotate inside of it. Having this metal insert in there helps a lot so that you'd have to like crush these little tabs of plastic or have to break those off, and that's much harder than just expanding this hole a little bit and having the hex spin. Um, so anywhere we have a critical application and you're trying to transfer torque through a printed part in a hex shaft, having those inserts helps a ton. Uh, Relatively standard intake kind of belting after that. So they get it powered from up here. They just have a hex shaft with a whole bunch of wheels. They're a little bit bigger here at the top, and because of that, they have to have hubs on them. Um, so these are plastic Vex Versa hubs that they had bolted through to be able to spin these wheels. And then they have a pulley over on this far side. This is actually a metal pulley, and they put just large plastic flanges on the outside of it. So they just added their own flanges. So this is one of the ways you could do it. You could also do this to a printed part. You could just cut polycarb and make the flanges bigger here if you have room. And so this goes down to another pulley on this shaft, and then they continue to have some more wheels here, and they have actually belts on both shafts here. Um, there's a variety of reasons where they could have wanted to do that. It's possible they were having some issues with one of the pulleys skipping off or something, and so this just adds redundancy. Um, you can also go to wider belts. That helps sometimes to keep the belt on. So instead of using 9mm wide belt, which is what they're probably using here. You can switch to 15mm wide, which is the other standard size that we can normally buy. But you could also go even wider if you wanted to. You can buy belts in pretty much any millimeter thickness that you want or width that you want. And so occasionally we've used a 30mm wide belt for things. Um, so it just kind of depends on what you're trying to do. But there's nothing wrong with having some redundancy there. Normally works fine. It provides some tension on both sides here. So if the shaft came out or something, you have some way to not have it just like fall either. So having the belt on both sides could help with that. Um, what are the other little bits of how this works? So um, on the top shaft here, we have our bearings. So this is how we get all those pivot mechanisms working correctly. So each one of these plates has a bearing inside it, so that even though this roller is spinning really fast, none of that motion is transferred to these polycarb plates. And then as it moves in and out, they're able to rotate separately because they're both on their own unique bearings. They are touching each other, so they have to be careful not to like clamp too hard to have too much friction between these two faces here. But that's relatively easy to deal with. And then the bearings are touching, but not the plates themselves, very much at least. And the motor has enough torque to overcome any small amounts of friction there. Lower down, we see that they don't have bearings for this lower pivot here. So instead, they have a bolt running through a small shaft bolted to it, and then this plate is on a bushing. So this bronze kind of copper colored piece here is a bushing again, or sometimes called a plain bearing, like we talked about last week. And so that lets you do that rotation, gets it a little bit lighter, a little bit more space constrained. So easy enough for them to do that there. They don't need to spin anything fast on that one. And they don't need a shaft going all the way across or anything to get in the way of the ball. Down here, they have a bearing inside the plate, and then they have these outer plates that are set up to help hold the bearing in place. So in CAD, these are like overlapping each other. In real life, this is just like kind of sandwiching um, the bearing flange. Let's see if we can see the bearing flange. So the bearing flange right here to this plate so that the plate can't slide any further or the bearing can't pop off. Um, you do have this bolted from this outside into the shaft in here, um, so that it shouldn't be able to do that. But the plastic plate could get moved out in theory, and this bearing can kind of pop out of this hole and go to the side. So having this flange here helps. You also get a little bit more structure. You get a little bit more stiffness because you have this metal plate here that's adding some stiffness to the polycarb. But still lets all the upper structure flex. So if anything comes in, if a robot came in and hit it from the side, you're not going to bend out here, but you're going to bend kind of up in here and at these arms, which still let you have a lot of compliance, right? It can move and shake without being permanently bended. So if you made this whole thing out of aluminum, if all of these pieces were aluminum instead of plastic, when you took a big hit, they would permanently deform, and you'd end up, instead of having a nice straight piece here, this would be off sticking at like a 30-degree angle or something, and now the intake's not going to retract right, the belt's not work right. You're probably not going to be able to intake the whole rest of the match. So a lot of times you'll want to use the material properties of plastic, that flexibility, to let you have a little bit of compliance out here. But then you still may want to have some metal plates, especially on like the belt runs, to help ensure that these stay the right distance away and your belts don't pop off or come disengaged or anything like that. All right, let's switch up to our indexer and launcher. Um, So what can we see here? Let's add the hood and the intake back quickly. All right. So as the ball comes up, it comes up these rollers, up over the bumper, in between the centering wheels. And so they ended up using some star wheels, or sometimes like entrapment stars, or different names for it. But a couple different vendors sell them. Andy Mark and West Coast Products sell versions of these. You can also print kind of version of these out of flexible filament. There are some teams who had success doing that. There's also teams who had success like molding their own. So you can like print a mold and then pour silicone and make your own versions of things like that, depending on how custom you want them for the different games. There's different ways you can do it. Sometimes it's a amount of like how much time do you want to spend on it, and how much do you find them important compared to just having like a roller or a wheel here or something like that. So it kind of depends on the game object and the exact design to whether you need something more complicated, um, or if you have one like these that are cots that you can buy for $7 or $8 a piece. Is it worth doing that over just making your own wheel, or do you need to go all the way to custom printing or custom molding your own solution? Okay, so as it comes through, the ball's going to ride over this. We're going to hit this beam brake sensor, so we know that the ball is in here now. And then it's able to go through both these little star mechanisms and kind of move here into the middle. And so what they're able to do here is they have a motor down on this side um, that is powering, what is this one powering? So this one's powering this roller here. They have another motor down here. Let's see. So this motor, this is the one I was looking for earlier. So that one is actually powering the hood, and I think there's another one there. This is actually the one I want after I go through way too many motors. Okay. Um, so this motor here is on a gear chain that we can kind of see. So they have the small gear coming off the motor, big gear to another large gear. So these two are what we would call idler gears. So the difference here, what's it doing? There it goes. So these two are actually spinning at the same speed since they're the same size gear. They're spinning at the exact same speed. And so the main reason for this is just so they wanted that extra bit of distance between the motor and this shaft um, to be able to have the belt start up here, right? So if they just tried to put this pulley down here, it would run into this gear. And so to avoid that, they added an extra motor, and then the other thing, or they added an extra gear, sorry. And the other thing this does is this powers this same central shaft here as well. Oh, this is also for reversing. I forgot about that. So it doesn't quite idle. So instead, this is powering this lower roller here. Now this gear is reversing to this one. It has a belt coming from it that is then powering this. So that lets these two shafts and star wheels spin at the same speed but in opposite directions, and allows it to be packaged nice and low. So the heavy parts, right, the gears and the motor, are very low to the ground. So that lets you keep your center of gravity really low, so that the robot never wants to tip over. The more weight we can keep low, the better on all of our robots. Um, and so you have those two being powered off that motor, so those can spin together and bring the balls in. And then on the other side, you have this motor here that's driving our third star. So the third star roller here is driven on a different motor, so that if we needed to, there are times where we can have the ball come straight through the system. So if we're on the blue alliance and we intake a red ball, we can bring it in, and then we can have this one spit out the red ball out the front. Or if we want it to go up, we'll rotate it the opposite way, right? We'll rotate it counterclockwise from this view and bring it up, excuse me, up through this one and store it up in here before we go to launch it. So that ball can basically get captured onto this plate and this roller. So now it's up and stored, and then the second ball that will eventually fire can get stored down here once it's the right color. But if it's the wrong color, we can keep pushing them out until we get the ball that's the right color. What are some of the nice things they do? So they have a little pulley guard here to stop the pulley from jumping off or for anything to run into that pulley. So that's just that holds the belt on here. Again, we can see them using the little hex 3D print inserts. All right, so yeah, so we have that pulley guard. Helps make sure that pulley can't jump off very easily or nothing can get caught in there. Let's see. Okay, so powering this roller over on that other side that we already talked about, we have the motor down here that just comes up to a pulley and is just a direct, this is the feeder wheel, it's what it's commonly called. So this is the wheel that's going to drive the ball actually into our launcher. So you want to have this be very consistent, spinning at a very consistent speed every time, so that when the ball comes in, you can give it the same kind of initial velocity, initial speed before it hits the very fast spinning roller up here that we're going to get to in a second. And that gives you a very consistent shot. If you were to just spin this at whatever speed, you'd end up having some balls go farther or some balls go too short or too long, just on how much velocity was imparted by this roller. So a lot of our goal anytime we're building a launching mechanism is to get a really consistent feed to the launcher itself that allows us to make the rest of the system consistent. Okay, so a couple of the other things they do, so they have some mounts here to protect the belts. So they have polycarb across like the sides of their whole mechanism here so that they don't have the belts exposed wherever they can. So those are all guarded. Things aren't going to fall inside. Things aren't going to hit anywhere. And then we can also look at how the movable hood works. So up at the top of this launcher, we have the ability to change the angle that the ball is going to fire out from. And so they do that with this very large angled rack and pinion or sector gear setup, depending on how you want to call it. So basically, this is just a portion of a gear that would have a very, very large diameter, right? The center of it's out here somewhere, but we only need this small portion. And then this small gear here is spun by a motor again, pretty far down down near the belly pan with this gear reduction, and then belted all the way up to here. So that lets them keep pretty much all of their motors down below 6 or 7 inches from the ground. And then they just use belts to push everything up, all the motion that they need up towards the top. So as this rotates, this is able to come down or come up. And both these parts are just 3D printed, so they're able to design these however they need and design in features for mounting them to the rest of the hood here. So there's bolts that would go through this, potentially all the way through with nuts on both sides. So you could have like threaded rod go all the way through this and then bolt on both sides. That's often what ends up being done here. I'm not sure if they did that or if they bolted to this plate directly. Either one's possible and either one works. Okay, so let's see how they actually do their launcher. So the launcher itself, Those motors are driven down here as well, so they didn't want to have the launcher motors up high. They wanted those down as low as possible as well. And so to do that, they have these two belts, and they built in a tensioner here. So they're able to tension the belt because if you have this like multiple winding setup, it's hard to necessarily get it exactly right, to be able to always have the right amount of tension. And something like this, where you're spinning it really fast, you may want it to have a little bit of a different tension setup. So they did that along with having um, a little block down here that my guess is that this block is bolted into place. So there's like bolts going through into this plate. And there's a bolt here, and this hole right here is tapped so that as you tighten the bolt from the bottom here and make it go up, it's pushing against um, this rod here. There'd be a spacer rod going through this, and so it's pushing against that. And then when you tighten that whole assembly down, it clamps into place. Um, so as this can go up, you can add tension to this belt, and you'd have pulleys and things, or you'd have a pulley or some sort of bearing or idler here, um, that would be able to spin around as that whole mechanism is moving. Up at the top, we have a very long belt, and so this is just a continuous belt. You can buy belts in basically any length, which makes them very convenient. On chip's being weird. Okay. Or my mouse is being weird. One of the two. Okay. So we have the pulley up here at the top. This shaft is powering their actual like launcher wheel setup. Um, and so they have 4 wheels here in the middle. That's what's doing their main launchers, or doing their main launching. It's going to put the velocity on the ball to send it out into the hoop. On the sides here, are brass flywheels. So they did want to use. They ended up using a little bit of weight here to give their entire roller here more mass. And so what that helps with is as that first ball goes through, once this is spun up to speed, as that first ball goes through, it's going to take away some of the energy that this roller has at that time. And so if this is relatively light, um, the wheel is going to slow down a decent amount. And so by the time the next ball goes through, the motor has to impart more energy to get it back up to the correct speed. And so there's kind of 2 ways you can do this on most launching games. It only really matters if you're shooting multiple objects quickly in succession. If you're only shooting one object at a time and you're gonna have to go pick it up again, to shoot it again, you're not too worried about this. Um, and so basically, if you don't have these weights here and you have a relatively light one, your motors just have to be tuned so that as soon as that ball goes through, the motors can impart enough power fast enough for the next ball, and still get it up to a consistent speed. So it does take a little bit more tuning potentially, but you can save weight. If you add more weight to it, the energy won't it won't be as easy, or you won't take up as much of a percentage of the energy, and so the wheels are already going to be staying at that same speed, and so you can get a consistent shot that way. Um, let's see. So their hood up here is what's known as like a powered hood. So these rollers here are actually spinning as well, so they're imparting some amount more energy into the ball. This was important this year because it ended up allowing you to have some amount of spin on the ball, but not too much. Because the way the game worked, um, this goal had plastic on the inside, and so if the ball was spinning too much, it would sometimes hit a wall and just kind of like ride up the other side and spit out, instead of actually being able to settle and go into the goal that you wanted. So being able to have these rollers up here took some of the spin away from the ball, but still allowed it to have some amount of spin. Um, and so some of that's based on the fact that the surface speed, so how fast any one point on here is spinning around, um, with these being 1.5 inch diameter and these being 4 inch diameter, um, these are under half the surface speed of this, so you're still getting some amount of spin from this as the ball exits, but this is taking away a decent percentage of that spin. Again, they have to do the reversing gears. They have the belt from this pulley up to the top one. They reverse it. Yeah, I think they're geared down a little bit. We'd have to look, but it looks like this pulley is a little bit smaller than that one based on quick look, but they might be the same. It doesn't really affect what we're talking about, so I'm not going to go into it. But you do get these all reversed and are all belted to each other on this side, so all three of these are able to spin at the same speed. And that's sort of the main way that they're able to launch. All of this whole hood assembly is mounted on bearings here. So there's this bearing on the inside so that it's able to rotate its position even if this roller is spinning really, really fast. The bearing down here isolates that rotation from this rotation, and so then this is what we often call coaxial. So they share the same axis of rotation, both the wheel spinning and this whole hood mechanism. But because the bearings there, those aren't going to affect each other very much at all, outside of like whatever frictions inside the bearing. But we don't really need to account for that. And so then they also have to have some things like these bars here so that the ball is able to roll up those even when the hood is not there. So they don't change too much of how it exits or anything. And all of those are also structure for their whole assembly, right? So these standoffs make it so that these two sides can't like bend in and or away from each other, so they can make this whole thing rigid enough. Similarly, they have some other plates up here to help do that. So this whole front sheet metal plate here does a good portion of that. It's going to make sure that this whole two structures aren't able to misalign from each other too easily. You can see what that looks like. So this is a full bent sheet that's kind of setting that angle and setting that connection between those two plate or the two whole side structures. Let's see. So they have a little bit of stuff here. These are just like LED tubes, most likely. So they'd have LEDs running on the inside of there, and the polycarb pieces there help act as diffusers to make them look a little less like individual pixels. And then let's look at Climber real fast. So I don't remember the team number because it's been a couple years, but Citrus actually got the idea for this climber from another team who had posted a video in the middle of build season. They just were like, hey, this climb's pretty interesting. And then Citrus developed it out further and added it to their robot. And it ended up working very well. So that's part of the reason why they have this main crossbar here, because the whole robot gets suspended basically from that crossbar. So you have the two climber plates here on the side that are bolted into that crossbar. And so when the robot's climbing, nothing is really mounted to that outside frame at all. It's all mounted to this center crossbar. These two climbing mechanisms are basically mirror images of each other. The hooks up at the top are slightly different based on how some of the latching and thing get done, just the way the climb sequence works. But the lower gearboxes and everything are identical. And so the basic concept is you have this gear chain, and you do have a pretty large amount of reduction because, again, these two motors are going to have to lift the entirety of the robot, and actually each one has to lift the robot on its own. Because when one of these is grabbing the bar, it lifts the whole robot up, so the next one can grab the bar. And so they have a lot of reduction to slow down this pulley here. In this case, this is a pulley that doesn't work with a belt, so this is like a spool And so it's going to have a cable on it that's wrapping to be able to pull down these arms up here at the top. Um, so they only are able to pull down, and so you need some mechanism to pull them up. And so we use a constant force spring that's not here in CAD, but the way it works is it'd be wrapped around this shaft here and basically mounted through this hole on the inside tube in there, and there'd be one on the other side. And so as that motor assembly, that gearbox winches out, as it releases string, those springs take up the slack and extend this arm up. And then when the arm gets pulled back down, the springs just get pulled down, kind of like a tape measure, and they can have the whole thing climb. Um, this is a pretty standard way to make a extending arm or like a climber arm of anything. You have springed up mechanisms and pull down just because you need a lot less force to raise these, right? You're not having the whole robot weight when you're just trying to raise these. They're only the weight of their own tubes and hooks. So the springs can do that totally easily. And then the motor is really just adding all that force to pull and lift the whole robot. The other part of this, so on the inside here, which I don't know if it's in CAD. Let's see. So they didn't actually CAD the inside, but so down here, there is a bearing block mechanism. I don't know if it's on the other one either. Let's see. Nope. Okay. Um, but there is a bearing block mechanism. So you have some internal bearings that are riding on the inside of this outer tube. And so at the full length, when it goes to grab the next bar or anything, they added these reinforcement plates so that those bearings, when they're on that inside of the tube and this whole thing is trying to like bend because it's taking the whole weight of the robot, these are able to like add some extra stiffness right to the tube where it's needed, and being relatively weight efficient to not have it bend or dent this tube at all, since you have this extra clamping force right there where the load of the robot is being transferred into this tube. Um, okay. So the other part of how this works is basically when they go to pick up on the first bar, um, this one here will go up, and as they're climbing, this little black piece and these little rods down here, this is a gas spring. Um, we talked about these last week as well. These are this is just a small miniature version of what's on like the tailgate of a car or the lift gate of a car. And so this is just assisting and always pushing up. So when there's no load on it, when the robot's not in a climb position, this is always pushed up. But as soon as you go to like lift and the robot's kind of hanging from it this way, the robot's mass is going to pull the arm in this direction. So then the robot ends up kind of hanging off like this. And now it's in a position that allows it to be ready. So we can get this kind of to pretty much to close to vertical here, somewhere on the center of mass of the robot. So like if this is the bar, you're going to draw a line between here and wherever like the center of the weight of the robot is, somewhere down here, I'd imagine. You're ready to actually extend this next one, and then this picks up a little bit. Um, and that's what lets you kind of seal this on the other side of the next bar. And then they pull this one down, pull the other one up, and then it releases that one, it comes back, and they do that whole assembly again, where this one's on the bar, and then this one can reach out and grab the traversal bar, and that's how they actually do the whole climb sequence. So there's nothing is powering these in and out except for the weight of the robot and gravity. So this mechanism works because they're able to understand the dynamics of how the robot's going to behave as it's doing the climbing, and they didn't have to add anything to specifically move these mechanisms at all. They just needed to have it in the right spot when the robot weight is pulling it to here. Um, and so that works pretty well. And so they were able to climb very fast that way. All of that was computerized, so they knew how far down they needed to pull everything and how far up. So it was all just a command sequence. Um, and so it was automated. They didn't have to have the pilots moving each of these hooks in and out or anything to be able to do it quickly. And that worked for them very well to have a very nice, fast, efficient climb. I think that's most everything on this robot. They do have limelights that were helping for aiming at the vision targets that year. They had the reflective target still back then. I don't think we missed much of anything else. Oh, there was one thing we didn't talk about. So down here, um, so this is the color sensor. So this is how they're able to know if it's a red or a blue ball. So they had a color sensor here, and I think at one point they had a mounting spot for one down here too. So I think that's what this is. I don't remember which one they actually ended up using. Um, but as the ball comes through, they were able to detect whether it was red or blue, um, and automatically spit it out, or whatever, however else they wanted to deal with it in code to determine if they needed to spit it out or not. So they did have a way to sense what ball, which game object they had in their robot, um, and move it up and out of the way if they needed to. So if it was the correct color, it would move up, and then if it was the wrong color, at some point they could spit it out. Sometimes they would spit it out in a current direction, somewhere farther from the other teams and things, so they could use that as a strategically for whatever they needed to. I think that is most everything about this robot.